Hubhopper Originals.
To start your podcast for free, log on to studio.hubhopper.com.
Hello, everyone, and welcome back to Indian Genes. I am delighted to introduce a remarkable guest whose work has quite literally touched the sky. And Roma Agrawal is not your average engineer. She's a visionary, an author, and a relentless advocate for the world of engineering. You may know her best for her contribution to the design of Western Europe's tallest tower, the Shard, a stunning icon of modern architecture that pierces the London skyline. But Roma's story goes far beyond that towering achievement. She's a product of two prestigious institutions, Imperial College London and the University of Oxford. Her amazing new book, Nuts and Bolts, deconstructs our most complex feats of engineering into 7 fundamental inventions: the nail, spring, wheel, lens, magnet, string, and pump. Each of these objects is in itself a wonder of design, the result of many iterations and refinements. Together, they have enabled humanity to see the invisible, build the spectacular, and communicate across vast distances. What truly defines Roma is her unwavering passion for promoting engineering and technical careers, especially among those who may face barriers to entry, and her advocacy has earned her international recognition, including the prestigious Royal Academy of Engineering's Rookie Award, and in 2018, she was appointed an MBE for her outstanding services to engineering. To all our listeners, we have an absolutely amazing conversation coming up with a very special person, and Indian Genes proudly presents a great conversation with Roma Agrawal. So, Roma, from everyone here in India and Indian Genes, a very, very warm welcome to you. Thank you so much for taking time out to speak to us. What you do is extremely interesting, and I think what you write and communicate is equally interesting. So I think we're very lucky to have you here on this podcast. But before we get any further, Roma, to people listening to you, is there something you want to tell them about yourself, what you're currently doing or involved in?
Yes, thank you so much for having me, and I'm so excited to be connecting with the Indian audience in particular because I've been living in the UK for 24 years now, and I still hold a very close place in my heart for India. But yeah, so maybe just a quick introduction. I have a very international upbringing. I've lived in the US and India and the UK. I even lived in the Middle East for a short while. I've also had a varied career, so I didn't know I wanted to do engineering, so I studied physics first. Then I went into structural engineering, and we can expand on that. And after that, after working in the construction industry for about 14 years, I then have completely changed my career, and now I'm doing writing and broadcasting, film, television, podcasts, and so on. All still to do on the topic of engineering. So I think the summary is that I've had a very varied life in different ways.
Brilliant. And I think for all of us who are not specifically from the field, we all know you as the person that was involved in building the Shard. And I think everybody has heard of the Shard in London. And maybe we could
Yes.
start there and then go back a little bit, but I want to get straight to that so people listening immediately know and can understand a little bit about your involvement in that building. And can you tell us a little bit more?
Absolutely. So the Shard was my second project as a structural engineer. The first project I did was a small, lovely little footbridge in Newcastle, which is in the north of England. The Shard is the tallest building in Western Europe, so definitely the tallest in the UK. It's on the south bank of the River Thames in London. Um, some people who might be familiar with London know that there are a few high rises in the Canary Wharf area, which is where a lot of the offices are. So, this is actually quite a unique location for a high rise building. And if you haven't seen it before, I mean, essentially, it looks like a pyramid that's been stretched upwards. So, if you imagine it's got a kind of a jagged base, about 8 to 9 sided shape at the bottom, and then if you draw some very tall triangles and then lean them in at about 5 or 6 degrees, you basically get the shard, which, yeah, so like a pointy pyramid. Now, of course, because this was the tallest structure in the country, a lot of what we did was quite pioneering. It was new, at least for the UK, and we did try and learn from other places around the world where high rise is very common and has been done before. And in terms of my specific involvement, I first of all spent a couple of like about 2 years just preparing the site for the new building. So that included demolition. Um, One of the biggest challenges of building a building like this in London is because it's such a big, busy city. We had, there's a hospital across the road. There's an underground train line just north of the site. There's one of the busiest train stations in the country is next door, and there's a bus station, and there's so many different interfaces that you have to deal with. So I spent 2 years doing that. Then I worked on the design of the foundation slabs. I worked on some of the design of the steel floors, which were for the offices. And then I guess one of the most exciting bits was the very top of the building. So we call that the spire. It's about 60 meters tall. It's a fully steel structure, and it's a fully exposed steel structure. So that was a really lovely piece of the building to work on.
Brilliant. And though it is obvious for anyone going into London, because you see it through the skyline, and we would definitely want to come back to this particular building and maybe talk a little bit more on high rises, Roma, with you a little bit later. But if we want to start at a particular place, then people who are getting introduced to structural engineering or trying to understand these huge, or in some cases not so huge buildings, where do we start as far as this particular construction is concerned? I know mythology tells us the Tower of Babel. We can always start there, but post that, when we come down to, probably, I do know that the Pantheon is one of your favorite buildings. So
It
does that
is, yeah.
does that become the starting point from when we actually started these gigantic structures? Because I think it would first came the pyramids, right?
Yes, sure. So I think just before we go into the history, I should say that not everybody knows what structural engineers do. I think particularly in the UK, maybe the audience in India is more familiar with engineering as a general concept. But my job is to basically use maths and physics to make buildings and bridges stand up. So that's what we're starting from, and this is a profession that has existed since day one. As soon as humans started thinking about creating something out of natural materials that wasn't naturally formed to live in, then you're basically a structural engineer. So if you think about, the early tents that people might have created, or the log structures, or they're just carving out from caves, or using stone, or using mud, these are all different forms of structural engineering. And I think in terms of the larger structures, it's not just height that we have done. We have done large structures in terms of scale. So that could be big irrigation systems, or, watering systems, which is obviously very important, or it could be palaces, castles. And I think those really came in when societies started organizing themselves, and then there was a power. So that could have been your emperor, your empress. It could have been some kind of king, or ruler, or even maybe a government. And it was almost then a way to channel funds and create these big statement pieces that signified something. And religion is another, I guess, great example. And in terms of height, of course, because I'm an engineer, I've drawn a graph. So we start with the pyramids were by far the tallest structure that humans first came up with, about 4 to 4,500 years ago. And the tallest one is the Pyramid of Giza, which at the time was 150 meters tall, roughly. And that, I think, I see, and it'd been great to hear historians' perspectives as well. But that was like seen as a stairway to heaven. It was seen as it was a spiritual creation. They want to honor their pharaohs. So it's that, how do you create that connection with God, or the sky, or the higher power? And so to do that, they built a very solid structure. So yes, there are some tunnels and ways you can move around the structure, but it's not designed for occupation. So the first structures that were tall and built for occupation, I believe, were from ancient Rome. So we're going back about 2,000 years. And they were building between 6 to 10 story apartment blocks that they called insulae, which is the Latin word for island. And these were built from brick, from stone, with bits of concrete as required. And they started to then have a lot of the similar problems that we see in the urban, like modern urban context. So that could be fire. So they had, well, it was a privatized fire system, which didn't work for the people at all. But that's a different topic. And they had the idea, like inequality became baked into it as well, because the most expensive apartments were actually at the bottom, because you don't have lifts, and so the higher you have to climb, the cheaper the apartments became. So the rich people used to live on the lower floors and the poorer people lived on the higher floors. So that became a very interesting kind of urban development. Then really we jump forward all the way to the medieval era in Europe, so like 1300s or so, when these Gothic, often inspired churches were built, and they built some very tall spires on top of them. But these spires were not always the most stable, and these got often knocked down by lightning or storms and so on. And so it's kind of amazing that for about 3,500 to 4,000 years, the pyramids retained their title as the tallest structures in the world. And it was really only when the Eiffel Tower was built in Paris in 1889 that we really smashed the record of the tallest structure. So that's about 310 meters tall. And then since then, we've had Manhattan, Hong Kong, Shanghai, all of these places around the world known for tall structures. And leading up to the tallest building currently in the world, which is the Burj Khalifa in Dubai. So that's 828 meters tall, if I remember correctly. So yeah, so now we've sort of gone a long way.
Very interesting. And just so that I can understand, from if we start at the pyramids, and probably those were the type of buildings that were built earlier, does a triangle shape, is it more fundamentally conducive to building higher structures as compared to the buildings we see today? Because if you see the shard, it also does encompass some triangles or angles there as compared to a
Yeah.
cylindrical or a rectangular structure.
It's a very interesting question, and I actually have a triangle tattooed on my finger because
Okay.
I just think it's such a wonderful shape, and it has other significance for me as well. But particularly in structural engineering, absolutely, it's a great question. The triangle is a great shape. So I'm, especially for your younger listeners, if you want to take some, I don't know, like toothpicks, you can take 4 toothpicks, and then you can put some gum or some kind of, you know, joining material at the 4 corners. And if you try and push one of the corners, that, the square will become a diamond and then it collapses very easily. But if you do the same with 3 toothpicks and create a triangle, you'll find it's much, much harder to deform that shape. So there is that inherent geometrical stability that the triangle encompasses. The other really good thing about the triangle is that its center of gravity is very low compared to a rectangle or a cylinder, because for a rectangle or a cylinder, the center of gravity is about halfway up. But for a triangle, it's only a third of the way up. So if you're building a big, tall structure and you keep the center of gravity nice and low, that means it's at less risk of destabilizing when it's being pushed or shoved by wind, for example, or by earthquakes or any other sort of movement. So, yes, the triangle is a great shape in that regard. With respect to the pyramids, it's also, I think, a matter of material, like how much material would you use? If that same 150 meters was created as a rectangle, you're going to use so much more material. And it would become much, much trickier to construct. And I think there was also this idea of, trying to draw your eyes towards the sky and create that bridge or link to that higher power. And so yeah, there are very many different reasons why the triangle is such a wonderful shape.
Very interesting. And if I actually look right out of my window now, there is a huge mall coming up, and it's supposed to be, well, I think it's going to be about 20, 24 floors plus. But all I can see for the last maybe 3 months or four is they seem to be digging downwards into,
Mm.
they seem to be digging. So I'm just trying to understand, as high as you go, how important is a good foundation, and how far does a foundation go? So if a to simplify it, if a building is like 10 meters tall, is there some kind of a ratio that the foundation should then be 2 or 3 meters, or is does it depend on other things as well? And how important is the foundation?
Yep. So foundations are incredibly important, and we talk about that in life, don't we? About whether we're talking about education or whatever else, that the foundation has to be solid. So that's 100% correct. Um, if we don't have a solid foundation, we end up with something like the Leaning Tower of Pisa. And I don't think many structural engineers would like people to come and look at their building because something has gone wrong with the foundation. So that's not something we really aspire to anymore. Um, in terms of, it's a very interesting question that you've asked about this kind of, is there like a ratio or a rule that we can follow? And I wish there was in a way, but unfortunately the answer is no, because it depends on the geology and the soil of a particular place that you're building. And this leads to the very interesting phenomenon as to why Manhattan and Chicago, for example, were some of the earliest cities that had high rise buildings, is because those cities are primarily based on rock. So you can almost just build a concrete slab straight onto that rock and then go as high as you want. And the rock is so strong that it just carries all the weight and the pressure and the compression, and there's nothing really a huge amount more that you need to do. So the foundation almost isn't a problem or a massive thought in these particular areas of the world. On the other hand, if we're looking at the Shard, which is in London, it's next to the river. The river has been around for thousands of years. It's been depositing a lot of silts, which have basically compressed and become clay. And clay, if you imagine just the same kind of clay that you would use to make pottery or something, the wetter it becomes, um, it expands, it becomes soft, it becomes obviously waterlogged, and then when it dries, then it shrinks, it cracks. And of course, these water cycles and so on are very natural throughout the year, throughout the seasons, and even in the long term. So, in a place like London, it's tough to build skyscrapers. So again, that's the reason why they weren't. We weren't well known for skyscrapers here, in the 19th century, like in the US. So we have to think a lot more about the foundations. And in the case of the Shard, the foundations go down around 50 meters. And again, that's not really linked to the height of the building, but it's more the fact that 50 meters below the ground level in London is a very strong compressed layer of sand. So that's a very strong layer. And what we're trying to do is kind of channel the loads. A lot of the load gets channeled through the clay onto this compressed sand, and then a lot of the load also is resisted by the clay itself. So so yeah, it's very much, we need to go deep, understand what the layers and geology is, and then design a foundation that suits that place.
Right. And you spoke about Manhattan that has a very strong rock foundation, for example. And maybe you could tell us, on the other end of that spectrum is Mexico City, because that is
Mm.
built on something that's totally not a foundation. It's a lake, if I'm not mistaken, and probably something that the Aztecs dreamt up, right? Is That's an interesting story. If you would want to tell us about that.
Absolutely, I love that story. So the Aztecs, so this is going back, I'm probably going to get the date slightly wrong, but somewhere between 500 to 700 years ago, the Aztecs were roaming the desert topology area of what is now Mexico. And the story is that they had a vision from their gods that they should build their capital city in a place where they saw a nopal cactus, that's a type of cactus, with an eagle sitting on that cactus, and then there would be a snake in that eagle's beak. So this is a very specific vision that was passed to them. And the problem was that they found this symbol in the middle of a lake. And so they said, well, now we have to build our city in this lake. And what they did was to actually build wooden stilts and then create platforms on top of that. So their city was almost above the water, right? So they kind of respected that the water is there, but they said we're going to find a way to create a city on top of that. And that's what they did. And they built pyramids and all sorts on top. And I'm sure that it was an incredible city. Then, when the Spanish colonists came in about the 15 and 1600s, they essentially destroyed that city. They then used the mountains around that lake to remove soil and put that soil into the lake to try and create a solid ground on which to build. And then they built what is now known as Mexico City. Now, of course, the problem is if you imagine taking a bowl of water, which is your lake, and then filling that with sand, you can imagine that sand is going to be, again, very wet, very waterlogged. And if you put buildings on top of that, they might start to sink over time. And I was lucky enough to travel to Mexico City. I think it must have been in 2015, 2016, something like that. And it really blew my mind because the structures there in the center of Mexico City, which is where the lake originally was, have sunk about 20 meters, if I'm not mistaken, in the last 150 years. So you can see the effect of this on lots of the structures. You can see some have settled a bit unevenly, they have tilted a little bit. You can also see that there's one particular statue with an angel on top, which was built by the Mexicans when they got independence from the Spanish. They put foundations down to the bottom of the lake. And so you can imagine that as the rest of the city sunk around, this particular tower, because it was founded well, actually became taller, which is very counterintuitive. And then they added some steps around it now. So you can see these extra steps that have been added leading up to the monument if you visit today. So yeah, it's a very fascinating thing for me because I think what it should remind us is that our history, human history, but also the history of our planet, our Earth, plays such a big role in how we live today.
It's an amazing story, and I think for people who want to connect it or are looking for this particular symbol of the eagle on a cactus with a snake, I think it's in the Mexican flag now, right?
That's right, yes.
And mentioning about talking about rather these buildings or these structures at these early times, were they mainly built with bricks? Was it bricks? Because I think in the Indus Valley it would have been bricks. Those were the earlier ones. But when
Mm.
did when did it then evolve into concrete much later?
So, in general, around the world, we built with materials that were easily accessible to us in the local area. So, as you say, Indus Valley, Mesopotamia, a lot of these civilizations used brick. They used mud mixed with straw, which we call adobe in some parts of the world. Um, so that's all local materials. Concrete had been used before the Romans. It's not very well documented, but the Romans certainly used concrete quite a lot. Concrete being the mix of some kind of powder that we call cement. That could be like a burnt lime, that could be ashes from volcanoes, which is what the Romans use. And then you mix that with water. And then we mix that also with what we call aggregates, which are small stones, in the case of the Romans, small tiles, broken pieces of tiles and so on. And basically these three ingredients come together and create this mixture to which is concrete. So the Romans used concrete and they used it very well. And we talked about the Pantheon very briefly. I love the Pantheon, one of the reasons being that it is made from Roman concrete and it has been so successful it's standing, 2000 years later. And it's a very kind of elegant structure. using the best properties of concrete, and the Romans understood that. At least in the West, the use of concrete then disappeared for about 1,000 years after the Roman Empire collapsed. And then you started to see concrete come back in the last few hundred years. But people didn't really like the look of concrete, they preferred covering it up and so on. But today, concrete is the second most used substance on the planet after water. And that is a really incredible statistic. And that is different. So whereas before we were using local materials, and so that varied across the world, now it seems that concrete has become a much more ubiquitous material that's being used everywhere, in a lot of the world. So yeah, it's a very interesting trajectory of how we use materials.
True. And the with concrete, does it have an impact of weather or depending on temperature? Because we do tend to hear that concrete could heat up or expand, and or rather, when it cools down, it expands. So, if you're building in concrete, do you, as an engineer, have to make any particular adjustments to or to cater to this expansion?
Sure. So all materials do what we're talking about, which is they change shape with temperature. So they tend to expand when warm and contract when cool, which is the opposite of what clay does in a sense because of the water content. So that's a little confusing. But concrete and steel have almost exactly the same rate of expansion and contraction, which is very useful because in the modern world, we reinforce our concrete with steel. And if you could imagine that if it gets very hot and the concrete is expanding in a different rate to the steel, then it would all just crack. But that's not the case. The steel and the concrete work very well together as a marriage of materials. So yes, we do have to account for that. We have to account for that for all different materials. But concrete, the reason why I think it's become so used across the world is because it is so robust, it is so strong, it can be built, um, constructed in water, and the degradation that happens is quite slow and can be managed. Um, it does pretty well with different chemicals attacking it, and it lasts a very, very long time. And the thermal properties are actually quite good in the sense that, at least in places like the UK or the more temperate climates where the temperatures are changing quite a lot from day to night. During the day, the concrete will slowly heat up, and then overnight it slowly releases that heat, so it keeps us warm. But then it's cooled down by the morning, and so then during the day, while it's hot, the building stays a little bit cooler. So yeah, it's a really great material in that sense.
Right. And when we talk about bricks that were used, for example, at the Indus Valley buildings, is it been the same, or have we changed the production of bricks or the way we construct our bricks? Have we added any materials, or are we doing anything differently from, let's say, the bricks of those days?
It's a really interesting question. I think, and just quickly, I should mention with concrete as well that, of course, it has a huge environmental impact, and that's something we can talk more about. But yeah, so bricks have actually not changed a huge amount in about 10,000 years. The most fundamental change is that we used to just dry them in the sun. So we would create a rectangular block and we would leave it in the sun and it would dry and it would become hard and then we would use them. And that's how, like the city of Jericho in the Middle East, which we found some of the oldest bricks, or in early Indus, that's what would have been done. And then at some point, we decided to actually fire the bricks. So we started heating them up to a very high temperature. And that actually changes the property of the brick itself. So whereas it's mud and it basically has the properties of mud if you just leave it in the sun to dry, when you fire it at a very high temperature, it actually turns more towards a ceramic or glass type of material. And so the properties are very different. Um, Other than that, I can't say that there's much fundamentally changed with bricks. It might be that we're using we can make the material a little bit more standardized. Our production processes are more standardized. Of course, it's now mechanized as well, so we have factories or machines producing it. But at its fundamental, it's that's the only difference.
Right. And then would you say that the next leap was with iron to be used for construction as a material? Because past all these, I think it relatively stayed the same. Like you mentioned, the material that was used for construction. But once we developed iron, I think up to today, are we using it?
So yeah, the Iron Age actually started in what is now southern India and Sri Lanka before it started in the West. So in the West, we were still using materials like bronze, tin, copper, these type of things. And in southern India and Sri Lanka, they started producing what is now known as Woods metal. And this was a particular formula of iron that they were producing, which was very, very effective. It was a good, strong material. It had good properties for corrosion and so on. And in fact, the Roman Empire was importing this Woods iron from the southern Indian subcontinent and using it in their structures, which I think is so interesting. And at this point, for honestly, for all the thousands of years of our history, metals were used in that quite modest way in structures. So they weren't making big structures primarily from this material. There are a couple of examples in China and India where there were old bridges made from iron, but these were very few and far between. And it was really only when industrialization happened in the 17th, 18th, 19th centuries, towards the end of those time periods, that we understood how to create iron um, in a big scale. We understood how to create steel on a big scale. So steel is basically iron with quite a specific carbon content. So it's a quite a low carbon content, and steel is a better material than iron in the sense that it is harder, so it has better it can resist more compression, more squashing loads, and it also has good pulling resistance. So if you like put it into tension or trying to pull on it, then it has a good robustness against that. But also very importantly, it's ductile, and ductility means that there's a little bit of give, a little bit of flexibility, so it doesn't crack very easily. Um, and so yeah, so really, to be honest, you can kind of almost see in the era of skyscrapers, that's when steel became the material of choice. Before that, we were using iron. We built the Eiffel Tower out of iron, for example, but it wasn't the ideal material in a sense. So that also has gone through a very interesting history and development.
Right. I'm speaking to you from Gurgaon, which is very close to Delhi, and we do have the iron pillar, which used to have the Garuda, right? It's
Yes,
not
yeah,
there anymore.
yeah. Yes, and I wrote about that in my first book, Built, um, that this iron pillar had been created, and I think it's moved around India a few times, but yes, it's in Delhi now. And there was a very specific kind of mix of impurities. I mean, I say impurities, but it's part of how iron is extracted from the ground, which meant that even though it hasn't been specifically treated to resist corrosion, it's actually resisted corrosion incredibly well. And it's still standing there, kind of surrounded by these really impressive, I think it's Mughal architecture in that particular case.
True. And I do want to get to the cathedrals and the buildings that came up in Europe at that particular time. But something that just stuck with me right now is you mentioned about, we were talking about the Leaning Tower of Pisa. And maybe I'm not sure, I don't know how many people listening are. So the tower is, it is in that angle because of a fundamental flaw. And how safe is it now that it is leaning, and is it, does it continue to extend its angle of of leaning towards the floor?
Yeah, so yes, it's a flaw. So basically, they built some kind of foundation, and then as they started building the tower on top of that foundation, something basically shifted underground, and there was a bit of instability. So the foundation started to tilt, and then the more weight they added to the tower, the more it started to tilt. And then they tried to compensate, and so the building I don't think is exactly straight. It actually kind of kinks, it bends a little bit to try and compensate, and that kind of worked for a little bit, but then after it was completed, it started moving more and more. Yes, it's safe now. Engineers have gone in and stabilized it, but they were also asked not to completely make it straight because then it wouldn't be such an interesting tourist attraction and it would lose its name, I guess, in a way. But yeah, so they've now found like a good angle that you can see, so it's still, it draws the crowds, but it is stable and safe.
Yeah, that would be weird if they had to change its name to the Straight Tower of Pisa.
To the straight,
So,
exactly.
yeah. And uh, Roma, with these huge cathedrals that came up in Europe now, we probably seen a new structure or a new design, and I'm talking about domes because domes were not
Mm.
previously visible. And as an engineer, is that design really difficult to conceive, or is what do you think about probably the architects of those days that came up with the dome? Is it like an amazing discovery?
I absolutely love domes. I think they're so beautiful. I mean, I love arches. So arches are the two-dimensional version in a way, right? So they could be a semicircle, they could be like a parabola, or different shapes, and then the dome becomes the three-dimensional version of that. And I just think they're such elegant structures, not only because of the way they look, but also because of the way they channel their forces through through its body. Um, so again, we know that the Romans had created some really big, beautiful domes, and so the Pantheon again kind of comes to my mind. And but I also think of the Islamic world a lot when thinking about the dome, because the Islamic architecture really created the biggest, most impressive domes, particularly pointed domes, so that there's a slightly different shape to them, and also the pointed arch. So we see a lot of these very tall, pointed arches on Gothic Christian cathedrals. And in fact, those were inspired by Islamic architecture because they were using them in their mosques and their palaces and so on. And the pointed arch enabled us to build higher shapes, I guess, and that kind of led to these cathedrals becoming a lot taller. And I recently just spent a few days in Istanbul doing some filming for a project, and like honestly, you can just see it's a great example of a place where you can see that Christian and Islamic architecture, that the confluence of West and East, and how beautifully the architecture developed over time there. So I think, yeah, it's always good to remember that all kinds of different influences can come together and create a really beautiful result.
True, I have been to Istanbul and it's absolutely stunning. You're right. So, Roma, with these constructions happening at that time, we are forming a very good timeline here. And if we now come to the evolution or the beginning of skyscrapers, how did that start? Because, right, we are talking about these buildings, but none of them were used for people to live in. They were not residential properties, but they started becoming offices and properties probably in the US. And why did it start there?
Yeah, so I guess the Romans had sowed the seed of this idea, but it wasn't maybe necessarily very successful, but it was definitely a way people lived. Um, a lot of different things had to happen for the skyscraper to become a possibility. So we talked about steel, we talked about concrete. These were two very important things. So the materials that we're using. Um, the other important thing was foundations, as we've also talked about. So as our understanding of geology and foundations improved, that made a big difference. Um, the lift is actually a really important one because I mentioned that in Roman times they didn't have lifts inside these apartment buildings, and so you're actually limited by the practicality that humans wouldn't want to walk up and down more than, say, 10 stories. So we needed that lift, but with the safe braking system. And I've written the story of Elisha Otis in my book as well, about how he invented this in 19th century New York. And the last one, which is also it's a slightly more maybe niche kind of subject, is the cladding of the building. So that's the skin of the building that we put on the outside. Um, we used to just build a wall, from brick or from concrete or stone, and then that wall would take the weight. But with the skyscrapers, if you did that, the amount of material would be so huge that it would become extraordinarily heavy and not very practical. So we came up with this different cladding system where we actually hung sheets of glass off the skeleton of the building, and that becomes a much lighter solution. And that's often why you see that a lot of these skyscrapers are covered in glass, basically. And I guess the last one is about the stability system. So, how do you keep a building stable against the big wind forces that are pushing on it? And if it's a big chunky structure, something like the pyramids, then it's not a problem. We don't even worry about it. But the taller, the lighter, the more slender our skyscrapers need to be, then the more we need to think about the stability system. So there were different developments of the stability system. And again, one of the great engineers I've written about is Fazlur Khan, who was Bangladeshi and he moved to the US in the 1950s and 60s. He was very well known for his designs, revolutionizing how the stability of buildings was created. And all of these factors had to come together in order for the skyscraper to happen. And that required money, it required materials, it required that political will and that power. And then it also required the engineering fundamentals of good ground and so on. So yeah, I guess it was in those geographies where all of these things came together that we saw the first skyscrapers.
Right. Interestingly, you mentioned you did write about him as well, Fazlur Rahman Khan. I think that is such an
Mm.
interesting story. So, people listening to us or anybody who's looking for inspiration probably would want to listen to more about or read more about him because he was definitely a very interesting. He was a very interesting story. But you also mentioned about skyscrapers and wind. Now, I do remember getting right up to the Petronas Towers and in Kuala Lumpur
Mm.
where you could actually feel a little bit of movement. It was scary because
Mm.
I didn't expect it, and I started wondering whether, okay, is this the beginning of something that I don't want to know about? But you spoke about wind. Now, what about, especially if you're talking about Southeast Asia or certain locations in the world, what about earthquakes? Do you build for that
Yeah.
as well, and how do you plan for an or how best can you plan for that?
Yeah, so I mean, earthquakes. I mean, we have seen such devastating earthquakes. I think one of the recent ones was in Turkey. And again, just having been in Istanbul, that's been very much on my mind. And I've met some incredible engineers there who are working on these kind of problems. But 100% earthquakes are a big thing that need to be looked at. And there are, particular areas in the world who are very susceptible. Luckily for me in the UK, we're not susceptible and we don't have to worry about it really. So you do have to think about how your buildings are constructed. You have to think about the way the loads travel through your building. You need to think about, well, if a particular column or a particular part of the building gets shaken or crumbles or destroyed, then that shouldn't cause the rest of the building to collapse. So we call that disproportionate collapse. So basically, the collapse should not be disproportionate to, like, the cause or the forces that are involved. Um, so you tie together the beams and the columns in a slightly different way to make sure that you have that flexibility and you can absorb more loads. And then the other big thing that is done is you can use an extra stability system. So I talk about the Taipei 101 building in Built, where they've got a giant ball at the top of the tower, so that when the tower is being affected by either an earthquake or a typhoon, that this ball starts to sway. And they've really looked at the frequency at which this this giant ball. So it's like 3 stories high. So that's the scale I'm talking about. How does it move so that it cancels out the movement that you're feeling in the building? You can also put springs at the base of the building so that when the ground is shaking, that these springs can basically absorb these big movements and then release it as energy and try to minimize the amount of shaking that the building itself experiences. So yes, 100% it's a really important part of the job of a structural engineer. Um, but in terms of you feeling the movement at the top of the Petronas Towers, it's normal, and people always look at me funny when I tell them that all buildings move, all skyscrapers sway, and what we try and do is to make sure that the sway is not so big or so fast that we feel that kind of seasickness feeling. So you might perceive that yes, it's happening, but it should have been controlled in a way that it's not very uncomfortable.
Right, it was. So I I probably just I didn't expect it. Let's put it that way. Because if I knew about it before
Yeah,
I
yeah.
went up, then you're ready for it. But it just got me thinking. And I think even with talking about construction and earthquakes, I'm not sure whether I read something somewhere about the 9/11 Twin Towers. And would that been any different for people in that building or for survivors if it was made out of any other structure of any other material? So for example, if it was either a little bit more concrete, or was it because it was steel and concrete that the heating or the collapse was more impactful?
Yeah, so I mean, again, this is one of those awful tragedies that took so many lives and has stuck with us for so long. And it did really affect the way we engineer things and think about the safety of buildings. And we have to learn from that, don't we? Like if there were mistakes made or things could have been better, we have to learn from that and apply it. So again, I've written about the twin towers in my book from that engineering perspective, and it's about protecting the escape routes better. So nowadays, I mean, the UK had been doing this anyway, and I expect in India, because concrete is used much more than steel, it's also the case that the escape routes are protected by concrete. That wasn't the case in the Twin Towers. It was a steel escape. I mean, it was basically an escape route inside like a steel skeleton with some boards, like boarding applied, and that board didn't survive the fires and the impact. And then the other big one is kind of what I touched on, which is when a particular column, say, is impacted and destroyed, that the loads or the weight of the building from above should find a different route that it can travel through. Because if it can't find a different route, then it causes collapse. If it can find a different route, then you might have at least some time, if not preventing the collapse. And so the Twin Towers had been designed for plane impact at the time, but it was a much smaller plane than the one that impacted it in the end. So the impact was much bigger, more dramatic. It took out more columns. And then, of course, because it was still so much fuel, the fires really had a huge part to play. So we've relooked at the fire protection aspect as well.
Right. And as we learn or as we move forward, compared to we started with bricks in the Indus Valley, currently, do we have any eco-friendly material that is being considered or being used? I'm not sure whether any of that was used in the Shard, but are we looking at new technology to help us with probably material that could be eco-friendly?
It's a very important question. So one angle is to try and make concrete as eco-friendly as possible, and there's a lot of research being done into that. And the area of concrete that uses a huge amount of energy is to create the cement powder in the first place. And so we're looking at how can we use different products. So one example is using so it's called GGBS, which is ground granulated blast furnace slag, and that is a byproduct, a waste product of the steel industry. So that was one example which we did do on the Shard, which is we used a lot of GGBS instead of cement. So there's a bit of carbon saving in that perspective. So that's one thing to do. The other philosophy is to actually go back to the natural materials. So going back to stone, bricks, and timber and wood to create our structures. And wood is a great material because it's renewable. You can create fast growing wood that can be used, and also because wood actually captures carbon as it grows. It's actually a carbon capture rather than a carbon creator. The challenge with timber buildings is, first of all, how strong can they be and how high can they go. But I know that there's a lot of research in places like Scandinavia and Canada, which are very rich in these types of timber. And I think they're getting up to 14, 15 stories, and Japan as well, in fact. Um, and they're looking at 14, 15 stories made from timber frames. And then the other big challenge is, of course, fire. So we're looking at how can we do that. Um, and then there are a lot of people who are actually going back to using these more traditional materials, like I mentioned. And so that's one aspect of it. And then the other aspect is not to demolish buildings. So, particularly in very busy places like, the big cities that we're familiar with, should we be demolishing buildings to create new buildings, or can we refurbish the building that's already there, make it fit for purpose? So yeah, so using more eco-friendly materials is one aspect, and then the other aspect is to think about, do we need to actually build new structures in the first place? Can we reuse buildings that are already there? So can we refurbish things rather than demolishing and creating new sources of carbon? So there's a lot of very interesting debates and thoughts moving forward. But yes, buildings are a very, very polluting industry, not only in their construction, the materials we use, but also during their lifetimes, whether we're heating them, air conditioning them, cleaning the water, taking out sewage, and so on.
True, and talking about sticking to environment and environmental concerns, again, I've got two constructions going on around me. So one is a huge mall, and one is a small two-story building. That's a private
Mm,
building. Now, what I can see is around the two-story building, there's a large community because they're building that building with there's cement and there's bricks and there's a whole ecosystem around that. But this huge mall has nothing around and it just keeps coming up. So I'm trying to understand, when you build these large structures today, are these pieces or parts of it being constructed somewhere else and then they're just carried here and put into place rather than doing it at the location? Because that seems so much more cleaner.
yeah. Yeah, so that's a great point. So this idea of off-site manufacture, which is the jargon term for it, is a good one, because again, so timber is great for this because you can create modules units in a factory. You can make it very accurate, you can have very high quality control, and then you can come and just quickly construct it. And so the environmental impact is much better because you're not digging up and causing vibrations and dust and noise and all of these type of things on a construction site as much. So yeah, that prefabrication is a very important part. And so what I find interesting, because I've gone on this journey of that size and the big and the scale and skyscrapers and all of this stuff, and my first couple of books were on that topic, and now I'm kind of almost interested in the opposite scale, which is the small stuff. So that's what nuts and bolts is about, is the small inventions that changed our world. And what you're talking about here with creating modules or prefabricated items or factory created modules and so on, kind of takes us back to that idea that we need to understand what the small elements of our world and technology and engineering is, and then we should decide how we want to get big again.
Right. And coming to nuts and bolts, Roma, I have absolutely enjoyed this book. So I think
Thank you.
anybody listening to us, it's, and I wanted to know from you how you did come up with this idea of a book like this. And I know you've picked up just certain items that you want to talk about. They're so fundamental, and I don't think we can talk about anything else if we don't first cover this. But why don't you tell us a little bit more about where did this idea come to you for nuts and bolts, and why did you pick these particular items to start with in nuts and bolts? And is there going to be a nuts and bolts too?
I mean, there's going to be a children's version of Nuts and Bolts, which I'm very excited about, but I don't think there's a sequel as such. But yeah, so I think it's a little bit about what we were sort of touching on, which is we've been talking about all these big things and so on, and then of course the pandemic hit, and we're all in these places, and our life becomes very inward looking, and I just started thinking about the stuff around me, and I started thinking, well, what is the blender actually made from, and what is my laptop actually made from, or my desk, or my building, or whatever. And then I would try and break down all of these objects into their components. And then I would ask myself, okay, so I can see screws, but what's more fundamental than a screw? And I got to the nail. Or I saw a spring and or a battery, and I thought, what does a battery actually do? It stores energy. And so yeah, that's like a type of spring in a weird way. And so I basically came up with this list of 7 items, which are nail, wheel, spring, lens, magnet, string, and pump. And my theory is that most things in our world are made from some combination of these 7 objects.
True, and you've also mentioned that the reason you chose to study physics was because you wanted to understand the building blocks of our universe. And with what you've just mentioned, whether it's the nail, the wheel, the spring, these, at least to us in our universe as we live here and dwell here, these seem to be those building blocks, right?
Yes, so yes, in terms of the physics, I had become very interested in atomic physics and quantum physics, and really interrogating the idea that we came up with the atom, and we said the atom is the smallest and most fundamental thing. And then we said, oh no, the atom is made up of protons and neutrons and electrons, but they're the most fundamental things. And then we started looking at string theory. And so it feels like that quest for finding the fundamental can almost go on and on. And I guess engineers are different than physicists often because of this I guess that practicality point where I said, right, what can I actually see and touch, and is a real kind of object that I can really look at, and what's more fundamental than that, what's more fundamental than that. I kept asking myself that question, and then came to this list of 7.
Right. And if I'm not mistaken, in your book, you, as far as when you talk about magnets, and I'm trying to think now whether it's a magnet or the spring, there's a very interesting quote you said about the 1960s in Mumbai, because I mean, I grew up in Mumbai, and I do remember that
Mm.
every time anybody would come home and say there's a telegram, that is
Yeah.
bad news, So I was just laughing to myself when I heard that, and when I read that, because that is so true.
Yeah, तार आया है ना, that's what people say. um Yeah, so that's the magnet chapter, and so this is where I feel like, just in terms of me as a writer, I've been trying to up my creativity in a sense. And I wanted to tell the story of the magnet, about the different communication systems that we have around the world. Because at the heart of our communication systems is magnetism and electromagnetism. And that is true not only for the internet and for our smartphones and all of these things, but it's also true for our earlier communication systems like the telegram, the telephone, and so on. And I just thought about the fact that actually, even just my family, so I grew up in Mumbai. I was there from age 10 till 16, in the 1990s. Basically, I was the decade I was there. And I used to see all these different ways in which my family used to communicate. And it really struck me that my grandparents' generation had telegram and telephone, and then the television came along, and then the internet came along, and now there's these smartphones everywhere. And so I told the story of magnetism as the story of my family and how we have communicated, through, I guess, 4 generations.
Right. No, it's very interesting reading. And also, coming to another item that you spoke about there, which is the wheel, something as basic as the wheel. And I've always been thinking about this, but again, thanks to you, it just never struck me, because I always thought, okay, who actually invented the wheel, or who was the first guy? But I now get it when you speak about pottery, right? It was first invented for
Mm.
pottery, and so it was, and I was connecting that to something else. Most of the time, oh, I don't know if this is just my mind going in different directions, but we tend to build in 2 dimensions. And the moment we move it to the third dimension, so somebody would have moved that wheel up and then rolled it. And the reason I'm saying this is because we also find a lot of old obelisks still in Egypt that are on the floor. So you build it
Mm,
in 2D, and then the moment you move it into the air, that gives it another dimension. But the wheel is very
mm.
interesting for me as well.
I love that observation. I think it's so insightful, so interesting, and yeah. So people don't often know that the wheel was actually well, wheel and axle were invented for the purposes of pottery, and it kind of makes sense because gravity is helping you in that case because gravity will keep your wheel where you need it to, and so you had a wheel with a kind of a lump at the bottom, and that lump fit inside a dip, I guess, in a stand, and then you could spin it, and gravity helps you. But of course, if you just turn that on its side, then it's just going to fall apart. And so it took a lot more engineering and design in order to get to the place where we could actually put a vehicle on top of the wheel and use it in that way. Um, and I talk about this idea of reinventing the wheel in the book. So we went from the potter's wheel to having big wagons and so on, and those had solid wheels, so they were made from wood generally and was solid. Then we went to the spoked wheel, which is of course the type that you see on the Indian flag. We went to the wire wheel, so the spoked wheels used to be made from wood, then we started making it from wires, and that made them much lighter, so we're very familiar with those on bicycles. And then we created gears and we created gyroscopes, so that evolution of the wheel has been so fundamental to our progress that I find it very funny and strange that people say, "Oh, we shouldn't reinvent the wheel."
Right. And I just want to go through these items, and I don't want to give too much away because I want people to read the book. But coming to
Mhm.
the spring, and something that stood out in the book for me was the bow and arrow. Again, I would have never connected the bow and arrow to the spring, but you've done it beautifully in the book.
Thank you. I think that that is the most fundamental form of the spring, and if any of your listeners have other thoughts, I would love to hear those. But the idea of a spring is a flexible material that you can deform, you can change its shape, it stores energy, and then you release that energy to do something useful. Even if that is shooting an arrow to try and hurt somebody, the idea is you're using that energy for something. And when we think of the word spring, we usually think of, the coiled metallic spring, but there are very many different forms of springs, and yes, the bow and arrow is one of them. So I start with the story of Genghis Khan and how he established the Mongolian Empire. One of his most well used weapons was a very special type of bow, which was extraordinarily flexible and light.
True. During that time, when you spoke about the bow and arrow and it being connected to the spring, and you did mention it, it continues, right? Because from the bow and arrow, it then was used in a gun.
That's right. And so the gun has many springs in it, like whether it's a semi automatic pistol or a machine gun, there are loads and loads of springs that basically allow you to shoot bullets, right? And I think it's really important that, because as engineers, most of us want to do productive things and help people and create better technology, but we also have to understand that either our work can have unintended consequences, or that people can use engineering and engineers can use engineering to create things that are actually quite destructive. And so, we don't exist in a vacuum, we exist in society, and we really have to think about what it is we're creating and what the purpose of it is and what do we want the outcomes for that to be.
And interestingly, when you come to the lens, it is there's a very emotional letter there. So I'll let you talk about it.
Yeah. So I've addressed the lens chapter. I've written this short letter at the start of the lens chapter to my daughter, who's now 4, and she's an IVF baby. And the message I'm giving her is that she basically wouldn't exist had it not been for the lens, but also for the thousands of years of development, science, research, thought, ideas, innovation that came into creating the lens and understanding sight and light and refraction and all of these different things. So yeah, I think the purpose. I mean, it was cathartic for me. It was kind of like you say, an emotional experience for me to write that. But I also wanted to really make people very aware of how deeply embedded in our everyday lives engineering and science are.
No, it's absolutely beautifully written. Absolutely beautifully written. And it
Thank
was
you.
nice that
Appreciate it.
we had you to speak about it. And Roma, moving to the string, we all know the use of strings. We've used it all through our lives. But you being also interested in physics or have studied physics, we also have string theory. Now, is a string fundamentally the building block of nature? Because the more it vibrates, it provides a frequency to us. So a string is much more than a string in what we are talking about, right?
I think you've just given me a very amazing thing to think about more, to be honest. This is really wonderful to hear your perspective on it. I hadn't thought about it from that very fundamental place, but you're right, like string theory is now what a lot of physicists are looking at, and I don't know enough about it to answer your question well, but I think it's a very interesting thought and one that we should take away. What I've looked at in my string chapter was clothes. As you say, it's very much part of our lives, and specifically picked up the story of Stephanie Kwolek, who was an engineer chemist in the U.S. and who invented bulletproof vests, or the material called Kevlar, which created bulletproof vests. And for me, like I think about string, and we don't think about something that's so strong that it can stop bullets, but it can. I also talk about music and the story of the tanpura, which was a part of my childhood growing up, because I always liked classical music and I'm a Bharatnatyam dancer as well. And nothing like the tanpura exists in the West, so I also wanted to bring that story this side. And so I really loved speaking about that. And then the final connection I make is of the string is to the opposite extreme from the string theory of atoms that we're talking about to suspension bridges, because some of the biggest bridges and structures that we have in the world are made from cables that are very similar to the kind of string that makes our clothes, but obviously bigger, thicker, made from steel, much stronger material, and so on.
Right. And I think the last item you touched on is the pump. And in India, we all know the importance of that, especially when it comes to water and survival. Uh,
Mm,
how the
mm,
invention of the pump did, in fact, have a big impact on. We had people or women walking across villages to carry water on their
mm.
heads and come back with just with one pot of water. But the hand pump, if we call it that, solved that problem where people didn't have to go on foot to get water and come back, right?
Yeah, so I mean, the pump has been, again, one of those inventions that has been around for thousands of years because, as you say, water is so fundamental to our life, and being able to move water, which is essentially what the pump is, move water, liquids or gases, is is so fundamental to different parts of our lives. And yeah, it's interesting what you're saying. Particularly women and children were ended up having to go and get the water. And so, this kind of engineering stuff has implications on gender, on implications on a child's education, and, so many different things that, the effects of good engineering can, help address. So yeah, I talked about water. I talked about the astronaut suit, because they have so many different pumps in a suit that essentially allows us to leave the planet. Our bodies are not designed to go into space, but a pump allows us to do that. And then I also talked about the breast pump, which is a piece of technology that I use to help feed my child. And what I found really interesting is that the history of the breast pump design is all by men, and it's only really in this last 5 to 7 years that I could find any women inventors that were working on the design of this. And I just found that it was so kind of strange that a device which mainly women are using had not been designed by women until very recently.
That's very interesting because I think with a lot more of these designs, I think, or with a lot more of voices like yours, for example, what you're doing, the way you are communicating and reaching out to all of us, uh, we truly appreciate it because as non experts sitting on the outside, we may just have, there are so many opinions these days, and we talk about fact checking. It's always nice to get an expert online, and that's what we do here at Indian Gene. So, once again, I would really want to thank you for coming on. But, Roma, I know we've taken your time. Before we let you go, I have a couple of questions for you, and if you can take both of them together. One is, if there was one particular structure that
Mm.
you could pick out of all the structures that we've had from antiquity to today, what and why would, what is that structure and why that one? And
Hmm.
what kind of a message would you want to leave to people listening? There are students here, there is somebody who wants to get into structural engineering or physics, and what would your message be to people listening?
Thank you so much. So, the structure question I always find really difficult, and my usual response is the Pantheon in Rome. And we've talked a little bit about that, and I love it because it's a dome, it's very beautiful, it's geometrically stunning, and it also uses the famous Roman concrete, and they've used it really, really well. And it's a structure I've been lucky enough to visit twice now, and I really love that. So I will stick with that for today. And then, in terms of the message, I think we, between society and our people around us and even ourselves, we can place a lot of barriers on ourselves. We can have barriers placed on us by these outside forces that I mentioned. And so what I would just encourage everyone to do is to just maybe identify what some of these barriers are, and then just ask yourself, is that a real barrier, or can I challenge this, and can I do something a little bit different, and see where that takes me.
Great. And before we let you go, Roma, I think I'm going to end this podcast with a quote from you and your book. So, in quote from Roma to everybody listening, this is what you say in your book, that your hope is that you will reignite your childhood curiosity, that's for people listening, and inspire people to investigate the increasingly complicated black box of engineering in order to understand the building blocks of our world a little bit better. I just hope that people listening to us get a little bit of a glimpse into your book and what you are talking about, and I'm sure they will in future as well. But thank you once again, Roma, from everyone in India and everyone here at Indian Genes. Whenever you want to come back, we are right here next to the iron pillar. You can connect, and I
Brilliant.
just hope we can do this again.
Thank you so much for having me.
इस हब हॉपर ओरिजिनल को सुनने के लिए आपका शुक्रिया। अगर आप भी अपना पॉडकास्ट लॉन्च करना चाहते हैं, तो हब हॉपर स्टूडियो वेबसाइट पे रजिस्टर करें और 1 मिनट के अंदर अंदर अपना खुद का पॉडकास्ट लॉन्च करें। यही नहीं, स्टूडियो देता है आपको पूरी आजादी कहीं भी कभी भी अपना पॉडकास्ट लॉन्च करने की, सिर्फ 3 आसान स्टेप्स में। तो साथ में अपना पॉडकास्ट शुरू करने के लिए तैयार? जस्ट हॉप ऑन हब हॉपर, सिंपली कंटेंट।